Good afternoon, ladies and gentlemen. It's a story about what Carla very much liked, because a year ago I was in Mexico giving not the same talk, but a similar sort of talk for the GIFT workshop. And I was driving through the city of Mérida in the middle of the crater, and we started talking about the crater, and the taxi driver, Chicxulub crater, no lo creo. They didn't believe it because they couldn't see it. That's the main point. But if you go to Mérida now, I think they're establishing a new museum dedicated to the crater, so they're well aware of the crater underneath their feet. But today I'd like to enlighten you a little bit about the whole discussion of the extinction at the Cretaceous tertiary boundary. And 50 years ago there were many contenders. Sea level went up and down, climate went bad, diseases, mammals were eating dinosaur eggs. They were too tall to fit in the Noah's Ark and things like that. So all sorts of scientific and non-scientific explanations. But as it turns out, only two major theories survived. One is the impact in Chicxulub of the Cretaceous tertiary boundary, and the other one is a major episode of flood basalts in the middle of India. So I will bring you through the evidence of the extinction and the impact and the Deccan trap lava flows, and in the end you can make up your mind what is the more likely story. So first I'll start with the likelihood of impacts. You see, it's a very rare event. It's far from my bed, as we say in Holland. But they happen. As you look here are the orbits of asteroids still in space, and you see they cross the orbit of the Earth. So once upon a time they will hit the Earth and create a lot of disasters. And as they have in the past, here you see double crater, which is only 320 million years ago. Well, only, for us it's a very long time ago, but for life in general, it's not too far in the distant past. And just recently, in 1994, we have witnessed an impact of many comet fragments on the surface of Jupiter, creating a large size sort of pseudo-craters. And the size of this impactor of the comet was about the size what we think happened 65 million years ago and killed the dinosaurs. And the frequency of the impacts is something like this. Every 1,000 years we have a crater of 1 kilometer. Every 1 million years we create a crater of 30 kilometers. Every 100 million years we get a really big one. And the question is, we have found one in Chicxulub, where are the other 4? Haven't been found yet. So that's very intriguing. And on the opposite side is that, by coincidence or not, we have the extrusion of these huge pile of lava flows, one on top of the other, which are covering most of the peninsula of India. If you look here, this is a huge area covered with these Deccan lava flows. And as we'll see, they cover about the same time as the impact, maybe by coincidence. And we know that because if we look at the geomagnetic field of the lava stockpile, they start in a normal magnetic field, in the episode we call 30, and then the magnetic field of the Earth turned upside down, and we call it 29 reversed, which means that the magnetic field is reversed, and then we get another normal interval. And we know exactly when these dates happened. So we have a very good idea of what happens and when it happened of the Deccan traps. And as you can see, in the middle of these traps are some bigger soils and areas where dinosaurs walked around. You can ask yourself the question, if they're on the peninsula of India, they're not too large, shouldn't they have experienced sort of deleterious effects of the Deccan trap lava flows? And the other one is that in the upper part we see Paleocene fossils. So we know by several lines of evidence that these extrusions took place during or at the extinctions. And as you can see here, is part of the evidence of the Paleocene foraminifer, wedged between one lava flow and another lava flow, a little bit apart, but here are also Deccan traps, and we can see here the Paleocene fossils. And we have another means of transporting. It's a little bit complicated, but we use to trace the Deccan trap lava flows by way of osmium isotopes. It sounds complicated, but we know when basaltic rock dissolves in the ocean, the ratio between these two isotopes goes down, like here. And when there is a lot of terrestrial material from the continents, it goes up. So we have the same magnetic periods here, 30 and 29, and we see the ratio of the isotopes go down at the same time, here in Italy, in the Botticcione near Gubbio, in the middle of the Pacific Ocean, around the same time they go down, and if you compile it, we have good evidence that the dissolution of Deccan traps in the ocean has caused the shift of these osmium isotopes. So now we have a means of tracing the Deccan traps all over the world. And here again, we see the extrusion of the lava flows, several lava flows, and the changeover of the osmium isotopes from 0.6 to 0.2, which is very sizable. And we can trace it back in outcrop. This is one of the best ones. It's my own favorite. On the north coast of Spain, in the coastal cliffs of Zumaya. And you see here the succession of layers of the upper Cretaceous, and then suddenly, bang, we have the KT boundary. And we get similar layers, but much thinner, of the ocean floor in the Paleogene, in the Tertiary. And somewhere in between, we draw the KPG boundary line. But where are the Deccan traps? Where do they start? So we have to do some effort to trace back the osmium isotopes. Unfortunately, we do not have the geomagnetic field for a large part in these rocks, but we do have these very nicely, regularly bedded limestone marls. And it turns out that these marl and limestones are caused by the precession of the axis of the Earth, which wobbles around in a very complicated fashion. But they cause subtle climate changes, which causes the animals living in the sea to create more limestone or less limestone and more limestone. So we have a perfect way of tracing the geological history, approaching the KT boundary by counting these 21,000 cycles. And if we do so, we can also get these famous magnetic reversals and the osmium isotopes in time. So now we can trace the fossil records which we found here in these rocks back to the beginning of the extrusion of the Deccan traps. And is there anything happening? Well, very little. I'll show you a little bit later. But there is a slight rise in temperatures somewhere here in the rock record. It's actually found in the south of the Atlantic Ocean, but we traced it also back here in the Zumaya cliffs in northern Spain. So to me, it's quite unclear what the Deccan traps actually caused, and it's intriguing and very worthwhile to do some further research in that. On the other hand, impacts, I said it's frequent, and if we look at kind of the evidence for the impact, what should we look for? Well, here is a model. We see an asteroid approaching the Earth's surface, about 3.5 kilometers in size. It's about to hit the Earth. The yellow layer is water, the brown layer is sediment, and the rest is the Earth crust in layers of 2 kilometers. So when I set the whole model in motion, you have to follow what happens. And from these models, we can predict what kind of stuff, what kind of ejecta, as we call it, is thrown out of the crater and landed in the rest of the world. So here it goes. We'll run several times, 9 seconds, 11 seconds, 12 seconds, maybe even shorter. It runs several times, you can follow it. And the model predicts where the ejecta are. Here is the first hit. You see transient crater here, what we call in the first split second, it creates a crater depth of about 15 kilometers. And when it rebounds, it causes the layers to turn upside down. And it also causes here a huge tsunami, which rolls over the surface. And in the first jets, you see tektites shooting out of the initial hit of the crater. So it looks quite complicated, but we can fairly well predict what kind of stuff comes out of the crater. So here again is another model. We make shells of vaporized target rock, melted target rock, and shocked and partially melted. And surrounding it is the crust, which is also shocked, but which is not shown here. And coming out of the crater is a whole zoo of ejecta, which we found all over the world. And I'll get you through all these ejecta from far away from the crater to quite close. So we see parts of the fireball, as we call it, the very high pressure, very high temperature, vaporized middle part of the crater, which produces small spherules, microcrystites, some shocked minerals inside what we call the fireball. So what do we see? All over the world, we see the products of the fireball, which is the high pressurized gas in the middle of the impact. And when it expands, this hot gas explodes and then condenses again. So we see the condensation products and the totally vaporized bolide all over the world in all these locations. So we'll first have a look at that. And then there is a ring around where we can find so-called the melted objects, the tektites, in the sort of area around here. The far away is in Spain and in the middle of the Pacific Ocean. And even closer, we get what we call very proximal and proximal ejecta, which look very weird, like accretionary lapilli and some closer stuff towards the crater. So let's first go back to the original discovery of the iridium anomaly. This is the famous gorge in Italy, near Gubbio, and this is where Walter Alvarez worked, and I worked exactly the same time in southern Spain, which I'll show a little bit later. And what do we see here? This is the ancient Mediterranean, which we call the Tethys, a very deep part. It's about 1,000 to 2,000 kilometers or meters deep in the ocean, and these are the bottom layers of that former ocean. And here is the Upper Cretaceous with layers with a similar size. You see here the precession cycles, similar sizes in Spain, followed by the Paleocene on top of it. And always in between, whether you go in Spain or Italy or anywhere else in the world, you are able to put a knife in the rocks and say, this is the KT boundary. So that means whatever transition we have here, it has to be very, very sudden. And if we zoom a little bit in this top of this white layer, we see what happens. This is about 5 centimeters in diameter, and this is the clay layer where we find huge amounts of iridium. Well, why is iridium important? Because iridium is not part of the crust of the Earth. It sits down deep in the Earth. So a large amount of iridium, way above the predicted amount, it's the same what we have found in Spain. This is another picture in the south of Spain. This is Gubbio, this is Spain. And there, the clay layer is not a skinny 2 millimeter thick, it's 10 centimeters thick. And at the very base of the layer, this very green layer, you see a thin 3 millimeter thick layer of ejecta. And this is the layer which contains all the evidence from the Chicxulub impact. So let's go through all the evidence we find in there. Iridium is important because we have iridium in the Earth, but it's safely in the core of the Earth. We never can get to it. So even on the surface, we don't find the iridium because everything we had in the past is locked up in the core of the Earth, and there's no way, even with the deepest volcanism, you can get to the core of the Earth. That's different from an asteroid because the iridium, which in the Earth sits in the core, is spread out over the whole asteroid. So in contrast, an asteroid is very rich in iridium. That's the main reason why initially iridium was taken as the prime evidence for an impact somewhere on the world. But there is more to see. If you look in the same layer, there are what we call microcrystites. And these are tiny spherules, very tiny, which are probably condensed from the extremely hot fireball which is expanding over the entire world. So let's zoom a little bit in detail. This is the same layer blown up. This is in south of Spain, in Caravaca. This is in Agost. And you see that it's literally filled with tiny spherules. Some are altered to feldspar. These are altered to pyrite. And this is from a layer south of the Caucasus. You see the layer is even graded. The smaller ones on the top, the larger ones are at the bottom. Also 1, 2, 3 millimeters. Well, of course, you're all high school teachers. Well, do the calculation. If I have a layer of 3 millimeters around the globe, how much is that? In cubic kilometers. I mean, well, that's a lot, I tell you. It's more than Mount Everest squared. It's about 800 cubic kilometers of solid rock material, 800 cubic kilometers. In the form of these tiny ejecta alone, iridium and all that sort of thing. So once you've done the calculation, you know the energy of the impact should be enormous. And we indeed see that. If you look in the interior of the spherules, you see they're all crystalline. While their fireball is expanding, it cools down, and just like a rain cloud against the mountain, the cloud will condense, and a sort of raindrops, in this case made of solid material, will initially form droplets, and then it cools further down, and when it cools further down, you will see tiny crystals, in this case of kleine pyroxene. It's a very well-known mafic mineral which grows into the glass, but the glass has been etched out in this case by the seawater in the Pacific Ocean. So as soon as you found these, what we call microcrystite, that's prime evidence for the very hot part of the fireball of the impact. And maybe by coincidence or not, entrained in the fireball, we find tiny crystals of quartz, which we call shocked quartz, because these lamellae you see in there, normally when you look at the quartz crystal under a microscope, you see a homogeneous, well-colored crystal, but nothing of these lamellae. And these lamellae, if you look closely under another microscope, you will see that they're made of pure glass, because the crystal lattice of this quartz crystal is turned by the energy of the shock wave into a solid glass. The crystal bonds are totally disappeared. So that's good, and we call that shocked, a sort of sound wave passing through a signal, and it's very good evidence because there's not a single volcano where you can find these lamellae in any kind of quartz crystals. So next, from the outer zone, not the vaporized zone, that's the small spherules and the microcrystites and the iridium. In the next zone, also under high pressure, and it will also be ejected from the crater, do we see what we call tektites. It's splash form, and they're siliceous. They formed of the upper crust of the impact site. And we know them from other impacts because they're well known at amateur markets where you can buy them, but they're much younger. And this is how they look like. And they occur within this circle in the globe. And the best places are in the Gulf of Mexico. And there you see a sphere like this. It's pure glass. And at the upper surface, and you see a bubble inside. And I try to measure the pressure inside the bubble because it's still original. And as it turns out to be, the pressure inside the bubble is absolute vacuum. And I crushed them under a microscope between two glass plates with a video camera on top. And as soon as you crush the bubble, you see that the liquid fills the space entirely. So you know there's absolutely no air pressure inside it. This means that this whole spheral, molten, etc., has been jetted out of the atmosphere and fell back on the surface somewhere. So it cools down and solidifies out of the atmosphere. That's where it creates the vacuum and it falls back on the Earth. And when it falls back on the Earth, it creates an outer surface which is a little bit altered due to the shooting star illumination of these tektites. But they're typically, and they're found close to the crater. The farthest away you see here in the western interior, and I'll come back to that because that's important also for the record of the dinosaur extinction. And there you can see, this is my finger, you see a 2 centimeter thick layer. This is Philippe Clay's pointing to a similar layer. This one is both in the Raton Basin, right here, but also up to Canada, we do find this layer somewhere in a succession with dinosaur fossils underneath and mammal fossils above it. And if you look closely at this layer, you see it's 2 centimeter thick, not the 2 millimeter. So in that sense, we're approaching the impact somehow. You can see that the layer is always divided in two. There is a lower layer, which is filled with these tektites, the melted objects with bubbles inside them. And it's separated very sharply of another layer, which is full with the shock quartz and the iridium. So actually, what we have a dual layer all over North America. So it's a very typical product of the impact. And if you look at the trajectories of the tektites, they are jetted underneath and they fall first, they're larger. But the iridium is vaporized. It's a very small particle and they will sort of slowly fall down to the earth and the shock quartz comes mostly with them. And it extends from Canada in the north of Montana to Wyoming to the Raton Basin in New Mexico. Over 2,000 kilometers you see a 1-2 layer, a 1-2 layer, a 1-2 layer, the upper one rich in iridium. So apparently that's very typical for the impact layer in North America. And even if we go to the other side, this was in North America, recently the ocean drilling program drilled a site in the Sierra Rise where we have the KT boundary and a very similar 2 centimeter thick layer, also with a lower layer graded with spherules and tektites in them and an upper layer rich in iridium. So these two are very typical for the impact. So that's farther away. Let's zoom a little bit more towards the crater itself. And as you can see here, this is a reconstruction of the Gulf of Mexico. The Caribbean is totally unrecognizable, still has to be formed. Haiti at that time was here, and now it's right here near Florida. So that's an active movement of the Caribbean plate after 65. But the Gulf of Mexico and the area is more or less the same at that time as it is today, be it that sea level was much higher. Here you see the ancient coast level, the ancient coastline. And in all these places, do we have evidence for the impact in some form or another? And even closer to the impact, we get even down to what we call the ejecta blanket. So here in Balok in Haiti, we see a thick layer, and now it's 12 centimeters thick with a graded deposit where we find all these glassy tektites with the vacuum bubble inside it. Even closer, within this area, do we find what we call accretionary lapilli. And we do not understand them quite well. They're made of carbonate, of limestone, and they're layered, one layer above another. And they have a cross-section of a centimeter, of a couple of millimeters. And they all appear very close to the crater itself. So they are not studied objects of an ejecta, but we don't know them very well. If we get even closer to the impact, this is very close to the crater itself. We have some very good outcrops here on the border river between Belize and Yucatan, where we can find what we call the ejecta blanket. If we're close to the crater, and if you look at the moon and all the impacts on Mars, you will see there is a sort of blanket of ejecta, 1 to 2, 3 radii outwards from the crater. And it ranges up to very thick, of kilometers thick near the crater, to about 60 meters in Belize and somewhat less. So it's a thick blanket which has moved outwards from the crater. And also from that one do we have evidence in a dolomite quarry on the border river between Belize and Mexico. And you can clearly see this is the dolomite with all the nice Cretaceous fossils in them, which got extinct, by the way, at the KT boundary. And we see with the sharp layer house-sized blocks in a very chaotic matrix of what we call diamictite, which is also full of glassy blebs. So if we zoom in the matrix, we see all sorts of blocks, limestone blocks, this is a hammer for scale, and green blebs of the same sort of bubbly glass what we found in the tektites. So now we know we're close to the ejecta blanket. And finally we jump into the crater itself. So we made a tour from a 2 centimeter thick layer in North America to a 10 centimeter thick layer to an ejecta blanket layer. Now finally we jump into the crater itself. Why did it take so long for the crater to be discovered? Well, like the taxi driver said, you don't see anything on the surface. If you drive there, you have no notion at all that there's something big lurking underneath your feet. And that's because the crater is half filled. This is when it impacted. This is more or less the situation just after the impact. It's half in the sea, it's probably quickly filled by seawater. And all the reefs, etc., and the sediments in there have filled the crater completely up to now. And we need geophysical methods. This is a geophysical gravity map of the crater to detect the crater at all. And here you see the contours of the different kinds of gravity. You're a little bit heavier in this part and a little bit lighter in that part. So the heavy colors are the red colors and the light colors are blue. But that's, of course, very picograms whatsoever. And they co-occur, especially in the middle, with huge deviations from the Earth's magnetic field. And that's probably because the center of the crater is that uplifted part. You remember that the transient crater. It's under enormous pressure and it sort of bounces back to the surface. And the blocks inside the center of these uplifted core of the crater are oriented in very different ways. And they bring with them remains of their own magnetic field. And that's why it's so chaotic. So this was the first solid evidence for a crater lurking underneath the city of Mérida, although the taxi driver in the middle of the crater here didn't believe it. But even if you turn to Google Earth, it's a nice exercise. You can see the crater. You do it quickly. And now you see it. And there is a nice sort of ring-like structure here. There are natural wells on this side, there are natural wells on that side. But there's a clear circular feature on the subsurface. And if you drive there, you can even see the rim of the crater because they're very peculiar, what we call sinkholes or cenotes, the cenote ring. They're confined to the outer ring of the crater. You don't see them here inside the crater, you don't see them outside the crater. No, they follow in a swath of 10 kilometers the center of the rim of the crater. Why? You see there's cenotes, they swim into it. And that's because if we look at the situation just after impact, it's filled by the sea, we see a thick ejecta blanket with very coarse-grained material, house-sized blocks, etc. And then it subsides slowly and it fills in by sediments. So this is sort of cartoon how you imagine that the crater fills up. And that's where the cenotes, the sinkholes, come from, but because this is a rubble pile of very porous material. And all these cenotes have originated in the Pleistocene during the ice ages, when sea level went up and down by 200 meters, up and down, up and down. And that means sea level percolated to the surface and back and down in this very coarse material. So we think the reason the cenotes are right on the rim of the crater, that's because there is a huge rubble pile of the ejecta blanket right there. And fortunately for us, the Pemex oil company has made, in the past, it's 30 years old, a core drilling into the crater. And of course, at that time, they didn't believe it was a crater. They believed it was a huge volcanic edifice. and they claimed that the melt in here was part of an andesitic melt. But we have the cores, and this is the core description. We have melt at the bottom, a breccia layer of back-faulted and back-slumped sediment filling the initial part of the crater, and then the back part of the crater with very typical Paleocene fossils in the lower parts of the later filling of the crater. And each of these black dots are samples from the crater itself. So back in 1990, we went to Mexico and we were able to sample nucleo number 19, and from Yucatan 6, you see here the breccia of loosely put together material ejected inside the crater again. And finally, at the very bottom, we have this solid melt rock. And the melt rock is important because they can be dated, as I'll show you a little bit later. Just outside the crater, we have new drill cores where you see granites and basalts and melt and pieces of anhydrite and limestone. I mean, everything what is down deep in the crater is thrown out of the crater and fell back to the earth in the ejecta blanket in the direct surroundings of the crater itself. And this is important because we can date by argon-argon methods. I will not explain it, but it's based on the decay of potassium towards argon. And the decay goes in a very distinct rate, and where you can measure the different elements, etc., you know the age of the rock you're sampling. And here are the 3 dates of the deepest core in the crater itself, and you see the ages are sort of 64.99 with a very small margin of error, 64.97 with again a small margin of error, again 65. So they agree very well on a very, what we call a stable platform. So we're sure that these are the right dates. And they have exactly the same age as these glassy tektites we find in Haiti. Here are 9 tektites analyzed by the same method and the same nuclear reactor by the same mass spectrometer. So the ages of 65.01 are overlapping to a large extent the ages of the crater itself. So now we had proof that this is the KT boundary crater exactly at the KT boundary itself. And then it gets a little bit complicated, because if you look at Chicxulub, where it fell, you see it fell halfway in the sea, and we have this huge ejecta blanket also falling in the deep Gulf of Mexico. And of course that has created huge tsunami waves. And all where you see the transition from the green to the brown, that's where we find the KT boundary, in the rocks in the surroundings. So we have looked at most of these places, and I'll show you a few of them here, especially in Mexico, where we do have evidence for these tsunamis. And since tsunamis by large earthquakes are nowadays very fashionable, I think that the study of these tsunami deposits will learn ourselves something about the mechanics or the frequency of the size, at least of the nature of tsunamis. Because this is how a tsunami does not look like. This is a wave which you see in the beach. It has a sharp front. If you have a surfboard, you're willing to run down there and ride the ultimate wave, and you expect if you go through the wave there is an end to it. Well, that's not how a tsunami looks like. And you see that here on the pictures. This is from Thailand in the 2004. A tsunami wave, first the sea retreats. Here you see the naked reef with all the fish splattering along, and people on the beach just see, well, they see a sort of surfing break wave. We have no idea how powerful and how energetic this wave is. Because there is, unlike a surf in the surf on the beach, there is a beginning to it, but the end of the wave is 100 kilometers far out in the sea. So that wave is coming at you at several meters, and there is hundreds of kilometers following it. And that packs an amount of energy which is way, way beyond any of these waves in a normal surf zone. So you can compare tsunami waves by 1 hour long tidal currents coming in, coming out, coming in, coming out. So the sediments on the seafloor, you expect to be compatible not with ebb and high tide movements, rather than what you see underneath big waves. And that makes a huge difference. So let's first look at El Mulato, one of the better places. Here you see again nicely layered upper Cretaceous layers. And instead of a skinny 2 millimeter or 2 centimeter thick layer, you see 2 meters of sandstone there. A very thick sandstone with the tektites at the base and iridium at the top, and directly on top of it we see the darker sediments of the Paleocene. So it's dead smack at the KT boundary, but it has several components. If we make a cross section through the sand layer, we see at the bottom these tektites. And we are here about 1400 kilometers from the impact. If you look at the time schedule, These ones come the earliest. They are jetted out of the crater. In a couple of minutes they're there and they're on the seafloor. Tsunami waves travel in the deep Gulf of Mexico with a speed of 500 kilometers an hour. So within an hour or two, they're there on the spot as well. So what we see, first swirls at the bottom, and then the fine-grained iridium is somewhere in the top of the wave deposits. And remember, iridium is very fine-grained, and these deposits totally vaporized. And it comes through long journeys through space, it jumps down again. So the whole tsunami history, which is a history of about 12 waves coming in and out, in this case, and then we see the iridium. So there is a good reason to assume with one impact and a tsunami wave we can explain the whole sequence of sediments. Well, that's at least what most people believe. But there are a couple of people who believe that, hey, we have one impact and there's sandstones and maybe they contain fossils in there. Maybe there's more time than just the tsunami waves, which I estimate to be 48 hours. And there are people who estimate there's about 300,000 years in between. And that makes room for, okay, maybe Deccan traps play a role. I don't think so, but we'll see. If we get a little bit closer, this was far out in the Gulf of Mexico, we get closer to the shoreline, you see that the tsunami deposits gets thicker and thicker with huge blocks. Here's Peter Schulte standing next to a huge block and topped by a sandstone layer which is sort of settled out of the very disturbed floor of the ancient Gulf of Mexico. And if we zoom in on some of the parts of this tsunami deposit, we can even see small dinosaur teeth of this small dinosaur in between the tektites in the tsunami deposit and vertebrae of mosasaurs. They're all, and here also you see small tektites in between. So at least the bones of the victims of the Chicxulub impact are present in the shorelines of Mexico and being swept up by the backwash and back currents of the tsunami waves. So it's very intriguing. Okay, so we have solid evidence for impact all the way down to the crater. It's the same age. What did it do to the extinction record? So I'll devote the rest of the talk to go back to Spain and Italy and see what's happening with the extinction record. Once again, we have the clay layer with the iridium, the Upper Cretaceous. If we blow it up, you see all these fossils, about 70 species of what we call planktic foraminifers, unicellular organisms with a calcareous skeleton. They die in huge quantities, and each of these dots is one of those forams. And they are one of the main victims in the ocean of the extinction event at the Cretaceous-Tertiary boundary. Because if you look at the layer just above it, we see only very tiny forms of only very few species. So it's a wipeout extinction without any warning before the deposition of the ejecta layer. I was working in Spain, and here you see the Spain layer again. It's a thick layer. Underneath we see all the forms, tropical specialized forms of planktic foraminifera happily living in the surface of the seas. And these forms are very sensitive for climate changes, temperature changes, salinity changes, whatever you do in the ocean. If one of the parameters in the ocean changes, the composition of the fauna will change, and it doesn't do that. And directly above it do we see smaller forams, very simple. Some of them may be survivors like these from the ancient stock underneath, but most of them are new. So if we look what I did under a microscope and you compute it all, I turn it horizontal, you see here the fate of these groups of foraminifera before the KT boundary, before the impact, and you see there is some variation in them. Maybe it's cyclic, but basically the major groups do go on all the way up to the KT boundary ejecta level. Then they go all extinct, and we see a new group with one survivor here, and new groups which are come and go very suddenly of these very simple forms. And they, of course, they see an empty ocean there. So they experiment with evolution. So it's my hypothesis that in order to have new evolution in the seas, you have to wipe out first the ancient stock, because the competition of that ancient stock normally would be way too high to allow this very rapid adaptive radiation just above the KT boundary. And that accounts for mammals on land as well as most of the organisms in the sea. Extinction is very important for rejuvenated or vigorous evolution afterwards. So what about the other beasts? We have a couple of them. Here are inoceramids, huge clams which are extinct nowadays. They're about 80 centimeters, and I had one of my students count the yearly rings on top. You see here very faint rings on top of the shell, and it turns out that one of these clams has an age of about 850 years. So that's a very old thing. It's just like a tree on the bottom of the sea. It sits there, it breathes very slowly, it has some overgrowth of oysters on it. But they go extinct well before the KT boundary, here again in the cliffs of the Bay of Biscay. So they cannot be the victims of the impact because they're gone when the impact happens. What about the ammonites? Well-known victims, they go all the way through with maybe a little hiccup just before the KT boundary, but all the species get through, and then at the KT boundary, except a few species in Holland, they got extinct, like the foraminifera. So once again, maybe a little evidence for the Deccan traps. Now if you go to the dinosaurs itself, here's a typical landscape in Montana: coal layers, overbank deposits, river channels, and a wealth of fossils underneath. Triceratops, one skull was found here. And above it we see the tiny mammals, all with teeth and jaws, etc. And in between is arbitrarily, at the lowest of these coals, the people who work there, paleontologists, have drawn the KT boundary there. But is it? So it looks straightforward. And what did they paint? What kind of extinction? And a couple of problems, because there are too many of these lower coals. Someplace there's one, someplace there are four. And please let the true one stand up and declare itself the KT boundary, because you have to choose between the four. And then there's a problem. The big dinosaurs are lying with their skeletons on the floodplains, not in the river channels. And the mammals themselves are confined to the deeper parts of the river channels, like here. So that creates a problem, what we call about taphonomy, the way they're buried into the sediments. These are all reworked, and these have died in situ. And that creates a problem, because this is the classical picture of the turnover here in the Hell Creek area in Montana. We see a slow decline of the dinosaurs on the floodplains, but very rapid towards the end. And here we see the disappearance of the mammals, old mammals, new mammals. They disappear before the KT boundary, and even importantly, new mammals, all of them placental mammals, and one of them is the predecessor of all the apes and monkeys, already before the KT boundary. So this is a sort of pattern you could call that it's compatible with the Deccan traps, which happen to extrude about here. Okay, but there is a mistake. What do? We have to do two changes. We lower the KT boundary because the lowest of the four coals turns out to be the KT boundary. Okay, and then these ones are found in the river channels, and these are on the floodplains. And you cannot compare the two, because rivers cut down into the floodplain sediments. So the actual age of a cutting down channel is younger than the sediments on the floodplains. And that's what I did here. I replaced all the fossils. And now, what do we see? Well, maybe the dinosaurs disappear a little bit, but there's no solid evidence for that. But now we see the appearance, the re-radiation of mammals appearing after the Chicxulub impact, and the decline of the older species also after the Chicxulub impact. So I would submit there is very little evidence left for a Deccan trap influence, but there's a lot of evidence for also the terrestrial communities to be influenced by the Chicxulub impact. So put it all together, maybe a little bit complicated. Here are the famous magnetic zones. This is the Deccan traps eruption. These are the osmium isotopes. And these are the foraminifera. They don't do nothing. Maybe 1-2 species. They go all extinct at the ejecta level. And afterwards they radiate very quickly, also during the Deccan traps. The ammonites, the inoceramids disappear right here. We see non-avian dinosaurs die at the impact layer, and the placental mammals start to re-radiate just after the impact. And this is a pattern which is, to my mind, not very compatible with the extrusion of the Deccan traps, except maybe one organism. And these are huge clams. They form reefs, just like the corals do today. And the reefs seem to disappear about 500,000 years before the KT boundary. So but they live on a little bit up till the impact layer. So they may have really been influenced by the Deccan traps, but it's just a very small minority of the whole group which got extinct at the KT boundary. So let's zoom again a little bit in to the boundary itself. Here we see the ejecta layer, the clay layer on top of it, and of course we measured oxygen and carbon isotopes. It goes too far to explain what they do, but basically the oxygen isotopes tell you something about the temperatures. We see the temperatures go up, and tells you something about the photosynthesis in the ocean. And what we see here is a crash of the photosynthesis just across the ejecta layer and very low productivity further on. But there's room for something else and a sudden cooling here, because between these two samples there are still 500 years of time. So within 500 years you still can do a lot with temperatures. And let's do it because here we have the help of the dinoflagellates. Well, dinoflagellates are a pelagic group. They have a whip tail, they can swim freely, but they also are photosynthetic. So they have plant, have animal. And they're able to protect themselves in these very sturdy cages, cysts as we call them. And that's a resting stage in the sediment. And when the spring comes, they come out of the resting stage, go to the surface, multiply, and in the winter they go back to the resting stage. And apparently their capability of forming a resting stage allows them to survive the impact and the Deccan traps. So there's not a single species which goes extinct at the KP boundary. So let's look what they do. Here we see the equator, Alkef in Tunisia, Northern Africa, Spain, Holland and Denmark. Here are the dinoflagellates from the north and the dinoflagellates from the tropics. And they're there, they're not going extinct. So they're the first ones to react on the after effects of the impact. And the first things they do is that the cold water species migrate to the first centimeters just above the ejecta layer. So I submit that we have evidence for the migration patterns of these dinoflagellates of a short-term cooling. I say question mark 50 years because that's the amount of time we come to. And afterwards we see the reverse. Tropical species go to Tunisia and subtropical species go all the way to Denmark over a much longer time span during the high oxygen isotopes. So we have cooling, we have warming, and what's the culprit and how does it compare to the Chicxulub crater? So let's go back because in 2001 we have drilled again the crater. We got a complete core there. I was part of the science team and it was chosen to be on the edge of the crater because money didn't allow us to go deep in the crater because it was too deep and too hard, the rocks there. And here we expected to have something of the target rock, something of the ejecta which fall back into the crater, and something of the filling of the crater. And that's exactly what we got. So here is the actual location of the drilling. This is again the cross section. We had the filling, part of the target, and maybe part of the filling of the crater. And the whole core is 1500 meters deep in the Hacienda Yaxcopoil, and we have indeed the filling of the crater, the fallback breccia, and we have something of the subsurface where the meteorite landed. And that's a very important one. So we have a crucial core segment here, which consists of a mixture of anhydrite, which is calcium sulfate, and 63% of carbonate. And if that vaporizes, you can imagine, this is estimated by Pierrazzo and Meloche to be 250,000 megaton of SO2 is degassed as aerosol in the outer atmosphere. And since we know that SO2 is a very nice reflector of sunlight, it bounces back the sun rays into space, you can expect to have some cooling. And if you compare it, the Pinatubo eruption is the largest eruption of the past century. It ejected not 250,000 but 20 megaton of sulfur, and it led to half a degree cooling over 1 year in the year following the eruption of the Pinatubo eruption. So I would submit that if we take it all together and this evaporation of the anhydrite plays a large role, we can expect, and you see a model, that in the beginning we get global darkness, maybe about 60 days or so. In itself it's probably enough to interrupt photosynthesis, but it will lead through the bounce back of the aerosols of SOx to reflected sunlight, and it became very suddenly cold. But not for a long period, because all the models predict that the aerosols will rain out within a period of 10 years, maybe 20 years. And then what happens? The atmosphere becomes saturated with the CO2 and other greenhouse gases, like all the rotting organisms. We have good evidence for a large-scale fermentation on the seafloor. There's no way you can avoid probably a greenhouse following the aerosol event, and it becomes warm. And maybe there's a little bit warming by the Deccan traps underneath. But I think the vast weight of the evidence points to the Chicxulub impact as being the main culprit for the extinction at the KPG boundary. and maybe a little bit for the Deccan traps. And I think I'll leave you to questions after this. Thank you.